Hello there, you're welcome to Physics 115, Mechanics and Properties of Matters. My name is Dr. Bello Said, your facilitator for this course. On today's video, we shall be talking about dimension and analysis, which makes our first module. On our first module, Module 1, we shall be talking about unit and dimension. Unit 1, Unit and Dimension. The following are the scope of today's video. We shall talk about briefly the introduction, then what are our learning outcomes, then the main content, then we'll summarize. At the end of today's video, you are expected to be able to identify the base quantities in the SI unit system. You should be able to name the most frequent and used prefix for SI units. You should be able to perform unit conversion using chain link method. You are expected at the end of today's video to be able to solve problems with the values of the most common metric prefixes, explain the difference between derived and base units, and be able to apply dimension analysis to find approximate relationship between physical quantities that describe a system. So let's get started. This unit focuses on the basic requisite language and analytical techniques that are specific to physics. The unit will include the fundamental knowledge of measurement units and the scientific notation, standardization of the unit, and unit conversion. So standard and unit. Science and engineer centered on measurement and comparison. Basically, physics is an experimental science. As a consequence, we need rules about how things are measured and compared, and how we need experiment to establish the unit for those measurements and comparisons. Experiments require measurement, and we generally use numbers to describe the result of measurement. Any number that is used to describe a physical phenomenon quantitatively is called physical quantity. So what are physical quantities? Physical quantities are measured in their units and compared with a reference standard. The unit is a unique name we assign to measures of that quantity. For example, meter represented with the symbol m for the quantity length. The standard corresponds to exactly 1.0 unit of the quantity. The system of units used by scientists and engineers around the world is commonly called metric system. But since 1960, it has been known officially as the International System, or SI, where SI is abbreviated in French as Système International. Talking about the International System of Units, the SI unit, there are so many physical quantities that becomes a problem to organize them. Fortunately, they are not all independent. For example, speed is the ratio of length to a time. So thus, what we do is pick out by international agreement a small number of physical quantities such as length and time, and assign standard to them alone. We then define all other physical quantities in terms of these base quantities and their standard, called base standards. Again, when you consider speed, for example, is defined in terms of these base quantities I mentioned earlier as length and time and their base standards. So what are base standards? Or what are the qualities that qualifies a unit to be a base standard? A base standard must be accessible, invariable, and really reproducible so that anyone needing to make a very accurate measurement can refer to the standard in the laboratory and communicate with other people. Now that we understand that there are base quantities and there are some physical quantities that are derived from these base quantities, then it becomes clearer for us to be able to categorize physical quantities into two categories. One, base quantities, and derived quantities. The corresponding units for these quantities are called base units and derived units. A base quantity must be defined in terms of a standard. Scientists, in the interest of simplicity, want the smallest number of base quantities possible, consistent with a full description of physical world. So in other words, a base quantity or a fundamental quantity is a quantity which cannot be expressed in terms of any other physical quantity. The units in which these quantities are measured are called base units or fundamental units. So we have about 7 base units in the SI system of units, and they are given in table 1. As you can see, we have length, time, mass, electric current, temperature, amount of substance, luminous intensity. These are the 7 base quantities, and we can see their respective units. For example, length in meters and is abbreviated as m, time in seconds abbreviated as s, mass in kilogram unit and abbreviated as kg, electric current as a unit ampere and represented as capital A. Our temperature is in Kelvin unit and abbreviated as capital K. Amount of substance has a unit mole and represented or abbreviated with MOL. Luminosity intensity has a unit candela and abbreviated as CD. From these 7 base units or quantity, we can derive many other physical quantities. As we move on, we'll be able to see that. An example of a derived quantity is speed, and speed is defined as the change in distance divided by time. And distance has a unit in meters, and time has a unit in seconds. So the base quantities here are what? Length divided by what? Time, and their units are given in meter and seconds. We can consider another example, which is acceleration. So let's represent acceleration with small a. And acceleration is given as a ratio between velocity and time. Just the same way we define speed, our velocity is also the ratio between distance over time. The only difference here is that velocity is a vector quantity, which we shall discuss later on in the next unit. But for now, we define velocity as distance divided by time, and we have our time component before at the denominator, so we have divided by time. So at the end of the day, our acceleration distance is represented by length L divided by time squared. As you can see, we are able to represent our acceleration from our base quantity, length, and time. So therefore, acceleration is an example of derived quantity that was obtained from base quantity, length, and time. Another example of derived quantity is force. We can represent force with capital F, and from our second law of motion, one of the topics we shall discuss in our future unit or module is second law of motion being defined as the product of mass times acceleration. So in other words, we can have our mass represented as m, where m here represents our mass, our base quantity, and multiply by our acceleration. We understand earlier that our acceleration is the ratio between velocity and time, which is the ratio between length divided by time squared. So far now, we are able to obtain F, which is our force, from our base quantity, mass, length, and time. So to define any quantity, whether base or derived, we can specify a rule or procedure, and this is called operational definition.